My name is Zac Sweers. I work at Uber on our mobile platform team, and I do a lot of open source work around code gen. And so today we're going to be talking specifically about annotation processing, specifically with regards to Kotlin and its language features. If you want to follow along with the slides, you can find them here. Hopefully, Speaker Deck's finished processing them. I'll give that 2 more seconds. And I also tweeted it out if you want to find that. So like most good talks, I decided to go to Twitter and solicit information from the community about what they want to see in a talk like this. So if they were an annotation processor or author, what kinds of issues had they had in the past that they wish they had known when dealing with Kotlin code, or if they were a consumer of an annotation processor, what did they wish the tools they were using had better understandings of. So I posted this and went to bed and came back the next morning to this. Kapt and its build impact are clearly a bit of a lightning rod, and while I'm going to touch on it here in this talk, it's actually a little bit orthogonal to the original purpose. So I decided to say I don't have any secret sauce to make it faster, but we can help offset the cost by trying to make processors more valuable and worth the time that it's taking. So at the end of the day, Kapt is just a tool to enable processing, and we want to focus on the actual tooling itself. As such, this talk kind of assumes a little bit of familiarity with writing annotation processors, or at least know a little bit about how the API works. Try to keep it really high level, so it should be understandable even if you haven't worked with it, but there might be some terminology that just flies over if you haven't seen it before. A quick read of the room. Who here has written an annotation processor before? OK, that's actually quite a few. Cool. So what kind of quirks am I talking about when I say we want to do processing in the context of Kotlin? If you use a Java-centric annotation processor in Kotlin, you've probably seen some of these quirks today. There's a lot of stuff that just works, but there's also a lot of stuff that just works if you recite the right incantations and eventually keep hacking at it until it works. Some good examples of this, if you've ever worked with Dagger, who here's used Dagger before? All right, basically the whole room. So if you haven't seen it, it's a dependency injection framework with a sort of familiar add inject and add qualifier, et cetera, annotations. And it's a very Java-centric processor. It works great with Java, but in Kotlin, it's not always so straightforward. So let's look at a few examples of this. So say I want to provide a list of tacos. It's a pretty straightforward provision here. I inject it somewhere, and seems pretty simple. That's very Dagger dependency injection 101. But this doesn't actually work. This will fail at compile time, and Dagger will say, I don't know how to provide this taco list because I can't find any provision. Or it might say the provision is not actually injected anywhere. And that's really weird. And if you go Google around into Stack Overflow, you'll eventually find someone saying, hey, just add this suppressed JVM wildcard here. And ta-da, now it all works. And you say, well, it's weird, but I guess we can deal with that. Let's look at a trickier one. So in this case, instead of providing a list of tacos, we are just providing a taco. Now, we want to qualify with a custom qualifier. So because breakfast tacos are the best kind of taco that everyone actually wants, we're going to annotate it with @breakfast, which is just a qualifier. Yet again, though, this is wrong. It could fail in one of 2 ways. It could fail at compile time, and Dagger will say something again about, hey, I don't know where to get this from. Or if you have another taco instance on the graph, it'll actually pass, but then you'll get that instance on the graph, and it won't actually get the qualified one. And this is actually a really scary one, because if it's the latter case, you don't actually notice unless you happen to be looking at your app and realize that this is not what you thought it was. And the gotcha here is that we actually have to put this field site target here for some reason. And this is, yet again, weird. One more example here, and this is my favorite one, and I'm sure anyone here that has done any sort of DI plumbing in their app has run into. So say I have a plain old network module here, and I have a static provides. So this is Java code. I've got a static provides to provide an HTTP client. This is fairly conventional Dagger. It's nice. It's static. It's stateless. Yada yada. Now, if I want to do this in Kotlin, obviously Kotlin doesn't have static in the language. So instead, you put it in a companion object. And now we have to move the function down into it. And we have to annotate it with @JVM static to make it static in Java for Dagger to pick it up again. Now, for some reason here, this doesn't work. And again, if you go Google around Stack Overflow, et cetera, and you'll find out, oh, just fix it by annotating your companion object also with module for some reason. And after, now it works. It's a little bit weird, but whenever you look at this in the IDE and you do a build, so the nice thing with Dagger is it's all statically linked and it looks fine. But for some reason now, this method shows up as unused, which again is confusing. And it's because under the hood, the Kotlin compiler, whenever you have a static function in a companion object, copies it, puts it in the parent class. So now Dagger is actually using the static method in the parent module and not using the one in the companion object. So the companion object was a module for no reason in the first place. And the whole thing is really kind of dumb. Kotlin is supposed to be pleasant and concise, but this is just weird and ceremonious. You want Java interop, but not Java catering. There's got to be a better way for this, and there is. But it starts with the processors themselves. So a quick refresher on how annotation processing roughly works. It runs at compile time. Annotations themselves in Java have existed since Java 5-ish. The APIs for them came in Java 6. Fun fact here, Java 6 came out in 2006, which is 12 years ago. Now that everyone feels old. It reads it into an intermediate bytecode representation. And specifically, it hands it over to you through these elements and types APIs. It can't modify code. You can only generate more code. And it can run in multiple rounds, which is to say, if you generate code that then has other annotations that another processor recognizes, it'll run those again in a later round. So when we look at Kotlin code through these APIs, So when we look at Kotlin code through these APIs, it basically ends up looking like a sort of pedantic, weird form of Java. It's valid Java, but it's, it looks like someone who is really, really worried about static analysis tools was writing it. And we'll see why in a bit. So when you're looking at this through the compiler, though, we're looking at it through these elements and types and whatnot APIs. So if we look at this in a very practical example, say we've got a person class. This person has a property name. Kapt will generate stubs of what this looks like in Java. So this is what a stub looks like. I know that's hard to read, but we're going to move that annotation for readability. We're going to come back to it later, though. So if you look at this, this is where I'm kind of getting at with the whole, it looks very pedantic. And it might not pass your text-style linter, but it is valid Java. It's effectively, it's an API-only stub, and that's why if you go look at your Gradle task or something, you'll see Kapt stubs doing this and that. And that's because it's basically dropping in a public API that it can then plug into Java C. Java C can run its annotation processing, run whatever is done there, and then it takes all that and plugs it into the Kotlin compiler. And this is all really slow, and that's why Kapt is slow. And this is the code that your processor ultimately runs over as well. So not this, this. And we want to try to see the Kotlin in through this code and somehow tease that out to the processor when we're looking at it. So how can we go about inferring something like this from this? Well, if you look at this today, you can kind of infer some stuff from here out the gate. Nullability annotations or the bean style naming properties are probably Kotlin properties. Or even the parameter name in the constructor is actually the name that it is in Kotlin. But what if we say have a default value on this name? So in the Kapt stub, this becomes this. Do you see anything in there that says, hey, this now has a default value for the name? It's not very easy to infer that from here. We just added a constructor. So not very intuitive. And sometimes you actually won't even get a clue in Java alone. So say we now change this to a list of names. So in Java, it's going to show up like this. But if we make this list mutable, though, the Java still shows up like this. And we don't know anything about that from the Kotlin side. So we might be giving it mutable entries and not really realizing what the difference is here. And there's a lot of other cases like this, too, like higher order functions, sealed classes, nullability, et cetera. So we can't trust the Java alone here. So we're back to here. Now, remember that header that I removed at the beginning? This is a metadata annotation, and it's sort of the secret to all of this. So it's generated by the Kotlin compiler on all Kotlin code, and it contains basically a brain dump of everything the compiler knows about the Kotlin language features of that given class. It's not a full replacement for reading the Java types directly. Rather, it's a supplemental thing. And basically, it's sort of there to plug the gaps, the knowledge gaps of what Kotlin features are there amongst all the JVM code. The Kotlin compiler also uses this under the hood as well. So if you import Kotlin library externally, it goes and reads these metadata annotations off the class files in that jar. So we'll dissect this in a bit, but let's take a look at the annotation itself. So it's a plain old annotation. It's only applicable to classes. And it has a number of fields with seemingly esoteric names. They're tiny names because, according to the Java doc, they wanted to minimize the size, considering these are everywhere. So the K field is the kind, and this refers to what kind of class it is. So 1 is a regular class, 2 is a file, 3 is synthetic, and there's a few others. Most of the time, you're dealing with just a plain old class. MV is the metadata version. BV is the bytecode version. The next is this obscure D1 field, where D kind of stands for data, I think. I'm looking for someone from JetBrains in the audience to nod at me. Please say yes. All right, yes. Yeah, so, and this is where things get interesting. So this ends up being the metadata in a binary form. Specifically, it's a serialized protobuf of literally everything that it knows about Kotlin of that class. D2 is an extension of D1, where it's just a pool of strings. Think like method names, type variable names, parameter names, etc. And these can be referenced by index from D1's proto and looked up as needed. So if you've worked with protos before, it should look fairly familiar. There's 3 others in here that I'm not going to get into today, but you can go look at the sources and docs if you're interested. Currently, metadata is internal. So it's not public, but it is going to be public starting in Kotlin 1.3. So if we go back to our example, we can break this down a bit here. So we've got a metadata version here. We've got our bytecode version here. Kind here, where it's a class, so it's type 1. We got our D1. This is the serialized proto. Fun fact, if you look at this in IntelliJ, it tries to actually render this, but it gets really confused, and it's mildly amusing. And finally, in D2, you'll start seeing the string pool of different things that you can look up. And these should look pretty familiar compared to the person class. So you can see things like, these are the binary/JVM signatures for parts of it, or the parameter name, or the property parameter name and its getter, and even tells you the project name. So in this case, my project was called test project. So how do we read this, though? Especially that proto. That's not something that's easy to reverse engineer, just eyeballing it alone. This barely even fits on the screen, and this is for a simple class with 1 property. There is good news, though, and that's that someone has actually done this. They built a tool. It works across every version of Kotlin, and they're hosting this conference. That's JetBrains. And that tool is the Kotlin compiler itself. So the compiler knows about all this stuff because it has to. All these protos ship directly in it. So if you look at this protobuf.java file here, that's a file generated by the proto compiler that's about 26,000 lines long and makes GitHub fall over. And all the serialization mechanics are in here as well. So loading them actually becomes fairly simple. All we really need is to pull off that metadata class from our type element during processing. And we can start loading this information directly out of the annotation instance. So, reading information out of an annotation, you say, that sounds like a match made in heaven for annotation processing. But there's another place that we can read annotations that's worth a mention, especially since we are touching a lot of compiler internals at this point. And that's compiler plugins. Compiler plugins are a core part of how the Kotlin compiler works. It's enticing as a code gen tool for several reasons, really. They're faster and incremental. There's no stubs generation, and it doesn't involve Kapt at all, so cue the applause from Twitter. But I'm really proud of this GIF. That took me like 3 hours, but it was worth it. But they're not a public API, and it's not just in the way that you can like pull it off the shelf and start using it like metadata, but it's one that's constantly breaking and undocumented. From the tools tech lead for Kotlin himself, there really was no plans for this. And there's some other considerations here as well. So aside from being undocumented and not stable, you might want to write a tool that maybe supports both Java and Kotlin as needed. And compiler plugins only apply to Kotlin code. They're really painful to write. So I wrote a demo compiler plugin to generate redacted toString implementations. You can find that here if you're interested. And there's a bunch of just weird things with it. Like a bunch of stuff doesn't index in the IDE. I had to kill the Gradle daemon every build to make it run again. The code gen doesn't show up in the IDE because you have to implement that separately. And I'm pretty sure that this doesn't work with the current version of Kotlin anyway. And lastly, the talk title I submitted for this was Annotation Processing in a Kotlin World, not compiler plugins. So don't at me. But if you are interested in learning more, though, Kevin Most is giving a talk about compiler plugins in I don't think that room's right. One of the other rooms. He's giving a talk after this. But if anyone went to the keynote this morning, my slide deck is now 4 hours out of date, which means it is wrong. And JetBrains announced that they are working on doing a stable API in the future. And so when that happens, we can revisit it. But for now, back to where we were. So we're going to talk about two libraries today. They're both fairly simple and sit on top of the compiler APIs, but they work in different ways. Both just need that metadata annotation. And the first and main one that I'm going to talk about is one called Kotlin Metadata. So Kotlin Metadata is written by Eugenio Marletti, there. So if you have any bugs, he's there, not me. And it's sort of really like the first of its kind. It packages in a shaded fork of the embeddable Kotlin compiler directly in the library, where the fork components are basically just extra API sugar on top of the basically proto-serialization mechanics that are shaded in. The underlying proto information all comes in, and it actually even has some stuff to manage grabbing the annotation for you. So if you're using it, rather than having to do this, it has a helper extension property directly on element that returns a Kotlin metadata class instance. So you can just go to your type element, call .Kotlin metadata, and you get the metadata back. It handles looking up the annotation, parsing out the fields, feeding that into this Kotlin metadata class, which itself is a sealed class of all the different kinds, where kind is that K property that we saw in the annotation earlier. And they're all lazily evaluated. So you can look at it as something like this, where you have a bunch of different types of like package metadata, class, file, et cetera. Like I mentioned earlier, most of the time you're just going to be looking at this class metadata. The other types are useful in very specific use cases, but if you're just peering inside a specific class, then this is usually what you want. So once you have this type, you can actually pull out its data through this cleverly named property called data. Class data itself is another API from Kotlin metadata that's just a holder for relevant parts of the proto. So when we call this data field, it actually kicks off that deferred deserialization of the underlying proto itself. And within class data, we can then just pull the proto directly out of it. So this protobuf.class, or rather the protobuf class that it's an inner class of, that's the same one that we saw on GitHub earlier. So we've just pulled out a deserialized version of that. And it contains the full Kotlin information for everything on that class. The other thing that class data provides us with is something called the name resolver. This is another one of the tools in the protobuf deserialization mechanics that are shaded in. And this is here to look through things in that D2 field, which has all the string pool that we want to look at. So whenever we try to look at a string in the proto itself, all it's going to do is give you back a int, and you use that as an index into this name resolver to go fetch strings for you. So we're going to go way back to our original metadata annotation example. So in here, this is our proto. This is the array of strings that we're indexing with our name resolver. And once you're in here, it's actually a pretty straightforward model API. The proto has all the usual proto boilerplate if you ever looked at it. So you see a bunch of things like builder with list or all sorts of weird stuff. But if you just stick with like the bean style getters, the top level API is actually really readable. So if you want to get a list of all the constructors, you just call constructor list, and it gives you back a list of constructors. Same with properties, same with functions. So if we go back and look all the way at our simple example again, say we want to know like 4-ish things here. We want to know the name of the property. We want to know, or the name of the constructor parameter. We want to know if it's mutable. We want to know if it's nullable. And we want to know if it has a default value. This is not the case every time. This is just, for example, up here. And with the proto, we can actually easily do all of this. So first thing we'll do is nav that constructor. In this case, we know that it's the primary constructor. And we reach into the class proto's constructor list and find the first one that is flagged as primary. Now, this is actually worth pausing on because this is an important part of how this metadata API works. So this it.isPrimary is another piece of API sugar that comes in the Kotlin Metadata Library. Every type in that protobuf class, so there's type, there's class, there's function, constructor, a whole bunch of other stuff. All of those have this flags int property, and you can check flags as masks on it to find out different sort of Boolean information that's reused. So it, in this case, is just a proto constructor, and this extension property is actually just shorthand for this, where this flags class is just a giant global class in the proto with all the possible flags for different Kotlin features. So think like internal, default values, sealed, inline, you name it. Basically, if it's a Boolean type thing and it's reused in multiple places, you're usually going to find a lot of that information here. So back to our example, we've got the proto constructor here. We can grab its values, in this case, the first and only one, because we know we only have one here. So we can reach into the value parameter list, pull out the name parameter. Now that we have that parameter, we can start reading off this information that we are looking for. So name is pretty simple. When you call getName, it gives you an index, and then we drop that into the name resolver, and it gives us back the string that that corresponds to. So name resolver, getString, name.param, nameparam.name, and there you go. For has default, it's similarly trivial. It's actually just a Boolean on value parameter itself. So nameparam.declares default value. Nullability is a bit tricky. So it's easy to look at this and think that it's a property of the parameter. It's actually a property of the type of the parameter. And this is actually really key. You really, when you start digging into this, you start really understanding how the Kotlin compiler thinks about these things. And it may not necessarily line up with how you've always looked at Kotlin code yourself. So we have to go through into the name param, get the type, and then ask it if it's nullable. Mutability is different, but in a sort of similar way as well. Mutability isn't a property of a constructor parameter at all. We can write it in nice shorthand like this in Kotlin, but this is actually, the name is corresponding to two different things. It's a constructor parameter and it's a property. And so right here, we're looking at the constructor parameter, but mutability is not an aspect of that. We actually need to go look up the actual property in the class and then ask that if it's mutable. So again, in this case, we're just going to shorthand it because we know there's only one. So we go and grab the first one. Oop, there we go. And we ask if it's mutable or not, or in this case, isVar. IsVar is another one of those flags, sugar APIs that comes with Kotlin metadata. In a normal processor, you would want to do some more intelligent matching of this, like finding the property with the same name as the parameter. But yeah. So that's sort of it. It's a very simple example, but I think it really actually demonstrates and shows a lot of how looking at metadata really helps solve this problem. A lot of those intrinsics in the Kotlin compiler as well, like interarray, collections, nullability, are more often only inferable by reading this sort of information. So that's Kotlin metadata. It's a great little library. I definitely recommend it. It's also used by popular libraries such as Moshi and Room. It's stable and unlikely to break, but it's not using any sort of official public API. That's where the second library comes in, cleverly named Kotlin X metadata. So you can find it here. It actually sits directly in the Kotlin codebase. It's a new library from JetBrains released a few months ago that's intended to provide a first-party support for reading metadata. It sits on top of the same compiler APIs that Kotlin Metadata does, and it uses the same flags APIs as well, but it offers a different main API that's visitor-based, and the intention behind that is that it makes it as lazy as possible. It also has a few other features that Kotlin Metadata doesn't, such as reading .metadata files. So if you ever looked at jar that's produced by a Kotlin project, you'll see these .metadata files in your resources. And if you're not careful with packaging in an Android app, they'll also go into your APK. Fun fact. And it also supports actually rewriting metadata during compilation, which I don't know what you would do with that, but that's pretty powerful. And that's all I'm going to say about it for now. The visitor API is actually quite a bit tedious compared to the value API that we were doing with Kotlin Metadata and the protos. And like I said, because it's intended to be as lazy as possible, and when we asked about it, it said, yeah, it's for more like constrained environments, and the plan is to actually write another higher-level value-based API that sits on top of this in the future. If you want to see what me and some people from Square put together as a prototype of what this could look like, there's a pull request on Moshi that you can go check out if you want. Next thing I want to talk about here is some case studies. So these are things that I want to cover, not necessarily getting into the nitty-gritty of how you can pull information out of metadata, but how you want to think about working with Kotlin code in your processor. Hopefully these will serve as sort of useful examples for how you can think about it. They are specific, but I find that these often, like hearing how someone else has approached the problem often helps guide whenever you look at it in the future for your own work. So the first one that I want to talk about is a project called Copy Dynamic. It's super, super simple. Basically, it's in regards to the synthetic copy method that you get with data classes in Kotlin. So right now, like if you want to call the copy method and replace certain values, you have to do them all by name. So this started a while back where some person on the internet was like, I wish I could copy, but with like conditional stuff. This is very Kotlin specific, but it's also very simple. And so what we want is to do something like this. So say we've got this taco data class. You have a set of seasonings that come on it, and you want to know if it's a breakfast taco or not. And when you use it with a copy dynamic API, it would ideally look something like this. So you create your taco instance with Old El Paso seasoning, and you then want to do a dynamic copy. And so in here, I say taco, copy dynamic. If it's breakfast time, I want to set the isBreakfast property to true. And so this is something that you can't do in the regular, well, this is a trivial case, so you probably could do this in the regular copy one. But yeah, this lets you basically have this whole block to go through and set mutable properties, and then those will be carried over and built into the actual new copy taco that you get back. So this itself, when you are calling into it, this closure is a high-order function extension, high-order extension function literal. It's a bit of a word soup, with an intermediate receiver where we can dynamically set these properties. Very Kotlin-y. You've got Kotlin set, you've got data classes, you've got copy, you've got extension functions, higher order functions, function literal with receiver, last parameter, et cetera. And the generated code for this looks something like this. It's a bit much for this slide, so bear with me. I promise it is actually simple. This first part is a generated intermediate holder that just has mutable copies of those same properties that we want to copy, and you give it a source. It copies over the current values of the source, and then when you call build at the end, it calls copy with the new current values. And then in this copy dynamic extension function, you basically have this function literal that you receive in as an intermediate builder. And then it instantiates the builder from the current taco instance that you're extending in this. You invoke the copy block on top of that, and then it returns a new taco. And that allows you to, there we go. Yeah, so that allows you to basically get the behavior that we saw in those in this API here. So to support this in an annotation processor, we just have a simple annotation called @copyDynamic. We look for that in our annotation processor. We pull out all these classes, and it follows roughly this decision tree. So first, we read out that proto. We ensure that it's a data class. You can use the flags API on the class to say, hey, are you a data class? We get the primary constructor, because this is what copy uses whenever it makes a copy. We read off all of its parameters, and then we also find all of their matching properties, getting the names, nullability, mutability, types, etc. And once we have all of that, we actually have all the information that we need to generate these intermediate and extension functions with KotlinPoet. Note that if you're working with Kapt, Kapt actually has a special location for generating Kotlin code versus just generating Java code like most annotation processors you're using today do. This is accessible via APT option called kapt.kotlin.generated. And that's sort of it. It's a super simple example, but it's something that, it's not easy to do this in Java, but it's something that you actually get some really nice features in Kotlin, and it's very trivial to implement once you actually have information about that metadata. The second library that I want to talk about is a library called Moshi. Now, this one is a lot more complex. It's a JSON serialization library, and I'm actually not going to really deep dive into it here for the sake of time and cognitive overhead. If I were to sit here and explain how Moshi works and then why we design adapters the way they do, the next speaker would probably like to do their talk. So I'm just going to leave the link here, and there's also an overview blog post that if you want to go and look at a significant non-trivial implementation of a processor that uses all this information, this is a great resource. And I'm going to put all these links at the end as well. Lastly, I want to go through basically some guidelines and close out on these. They're not strict rules by any means. They're just things that I try to keep in mind whenever I'm working in an annotation processor and try to let it guide the methodology to keep the keep the road sort of smooth. First and foremost, remember that metadata isn't everything. So I think I'm actually quoting Eugenio here when he told me this. It's just basically, you have to treat it as added signal. It's not the source of truth for everything. It's just there to fill in the gaps on top of the elements and types APIs that you already have. Most of what you're looking for is still going to be in the standard plain like Java-C annotation processor APIs that you get. Next is abstract your renderer. Now, what I mean by this is like annotation processors have a tendency to be a bit scripty. They're often not really designed with a lot of like architecture or anything in mind. You just kind of override the process method, and then you just kind of dump all your code there, and then you're good. And when you write a test for it, you just make sure the code compiles, and that's oddly effective for testing code gen. But if you want to actually have a processor that works well with both Java and Kotlin code bases, doing this out the gate will make that a lot easier in the future. And what I mean by that is basically abstracting out your model of what you're trying to generate for and how you render that out. So you should be able to basically say, if you want to generate Java code, you have a JavaPoet-backed renderer that can take in this model and generate Java code that supports that. Or if you wanted to generate Kotlin code, you should be able to take the same model and run it through that. This is something that there's not too many like good examples of this out in the wild, but I think as Kotlin continues to grow and particularly having public access to metadata, I think this will be really important going forward, because it's not like people are going to wholesale switch over to Kotlin. Or maybe they will. I suppose I should remember my audience here. Where was I on here? Yeah, so it can be a lot of work, but like I said, it keeps your options open for much later. Another thing to be mindful of here is mixed source sets. So longtime Kotlin users will know the two best ways to slow down your builds are Kapt and mixed source sets. If you're generating Kotlin code, try to generate 100% Kotlin code so you don't accidentally impose mixed source sets on your consumers. And this potentially goes both ways as well. If you have a processor that supports both, You maybe don't necessarily want to always default to one language or the other. Maybe the consumer has a mixed source set. Maybe they have totally Java code, in which case you don't want to then make a mixed source set by generating only Kotlin code. One thing that helps with that is you can just give them an option in your annotation processor. It seems like a little thing, but it makes a big difference whenever the impact for people is their build times. This is also especially important if you have generated code that is referenced from handwritten code, or generated code that references handwritten code. So you can create some pretty vicious cycles in this, where you can have, say, like auto value is a great example of this, where you can have Kotlin code, and then you have Java code that is generated from it, and then you have other Kotlin code referencing the generated Java code, and maybe some other code from there. And all those have to happen sequentially, which is not great. Next part is lean on language features. So it can seem like this is a pretty obvious thing to say, but from experience, actually, it's very easy to sort of fall into a pattern of, oh, well, now I'm generating Kotlin code. But when you look at the code that you're generating, you're actually kind of still thinking about it like a Java developer. And it's really actually important to try to lean on language features. These language features are a big part of why people love using Kotlin. And you can bring a lot of joy to your consumers by letting them enabling them with these new kinds of language features as well. If you're generating code, extension functions are great for adding functionality in a non-invasive way. If you're generating code that calls through to handwritten code, being able to respect and leverage those features like default values, named arguments, et cetera, are great too. Moshi in particular with the generated adapters is a great example of this, where we can support a full suite of named parameters. We can support basically having default values. There's some really clever tricks that go on there that allow you to do really neat stuff in Moshi code gen that you couldn't do in Java. It's also important to be mindful of quirks and caveats. So working with all this metadata, it's not free or without cost or consideration needs. So there's some really important things to be mindful of here. Like I said, it's not public yet. It will be at 1.3, but we're not there yet. Even then, though, say you're using Kotlin metadata, it carries the inherent risk of not using public proto APIs. At the end of the day, like, it's shaded, so it's not like it's going to break if you update your Kotlin version to a different one than it used. And it is a proto, so you should get free backward compatibility. But at the end of the day, you never know. JetBrains might come in tomorrow and say, we've decided to serialize everything to JSON instead. Did someone cough in response to that? That is a strong reaction. Another key consideration here is that it's not incremental. So if you've got an annotation processor and then someone inevitably wanders in and says, Gradle has incremental annotation processing, can you please update this? The answer is that it doesn't apply in Kapt yet. If you're working in multi-platform, this only works in JVM. There's no support in Kapt for multiple rounds-ish. I'll link a project again, I'll link a project at the end, again from Eugenio, but you can finagle this if you really want, but it's something to keep in mind. And lastly, there's varying degrees of build system support. So historically, like, annotation processing has meant that it would work everywhere for free. If you wanted to do like a Gradle plugin, then yeah, that only worked on Gradle. Or if you wanted to do gen rule in Buck, that only worked in Buck. But APT was like a sort of golden thing, like if I do it here, it will work everywhere. And that's not quite the case in Kotlin. It really only works in Gradle. Maven isn't that far behind. Buck definitely isn't there and is only really community supported. And I actually don't really know what the case is for Bazel. If you're generating code, getting sources linked or indexing the IDE can actually take some work. This actually didn't even work in Gradle, really, unless you manually did it until Kotlin 1.2.6-ish. And in other build systems, I've never seen that work. So yeah, that's another kind of important consideration. If you're working with something that you don't directly access, then that's not an issue. But if you're working with, say, something like Dagger, where you have to then reference the generated code, that can actually be really problematic for people that are not on Gradle. There's others, of course, as well, but these are basically the main ones that I'd suggest being aware of. And lastly, say I have a processor and I want to support Kotlin today. What tools should I use? And my honest advice and answer to that is Kotlin metadata, probably. When there's a public value-based API, then you should probably use that. But for now, Kotlin metadata works pretty well and is relatively safe. If you do need to read like the .metadata files, or you want to get your feet wet with writing your own, you can try out Kotlin X metadata. But like I said, the word from the developer at JetBrains is basically that it's intended for more constrained, low-level environments, and they have plans for something better in the future. If you're generating code, also check out KotlinPoet. It's nearing 1.0, and it's a really great tool for generating Kotlin code. The maintainers and I have also talked a bit in the past about broadening the scope of it to offer better tools for working with metadata. And that's it. Here's a whole bunch of slides. Like I said, you can go to the slides that I uploaded. I want to give a special shout out, actually thanking Eugenio as well. He taught me basically all of this stuff, so it really should be him here and me sitting down there. But I did buy him a beer, so I guess that counts for something. Yeah, that's it. You can find me on Twitter. I'll be around for questions after as well. Thank you.